That's to the election.
No welding today?
I know,
All right, so let's talk about some of these equations and how they're used and that kind of thing. So if this is a huge if we don't have school on Monday, the test is just going to be on Tuesday. So whenever we're together again, if we don't have school on Monday, that's when the test will be. So there's a possibility of that. So it's that. If nothing else, because of the test should be on Monday morning. Okay, so let's kind of talk about. There's two big ideas that I want you to get out of the beginnings of chapter 17. Okay. So one of them comes out of this idea of the double slit experiment. And what you can do with that in terms of wavelengths. So again, it's important that you look at what's in the equation and what's not in the equation. So on number 7, this is what I showed you all yesterday. Okay, so we took that sheet of aluminum foil, and I had taken a razor and I put two slits in it very close together, and I shined that light on it. And then when it showed up on the board, you had very, very bright lines, and then you had lines where there was darkness in between. So because of the fact that this is a double slit experiment, what happened is that you had light coming from each one. So the classic example of this is like I showed you on that quantum physics thing, quantum. And if it's like a water wave, and as that water wave goes through, because of interfering, you either have constructive interference where it's really, really bright, or destructive interference where it cancels each other out. And so if you look at, there's these two big equations, and there's different variables on here, but here's the basic idea. So this one, which is, and you have to understand what these are going to represent. And I'm going to go back and I'm going to try and demonstrate this here in a little bit with sound, so you kind of get an idea of what this is. So the delta y, that's the distance, and sometimes you see this written as delta x. It's the same thing whether you use x or y. So what this is telling you is the distance between the relative maximums on a double slit, and whether that's sound, whether that's any type of electromagnetic radiation, doesn't make any difference. Okay, so this is the distance between the maximums where you get this destructive interference. The value of m, unless you're explicitly told anything different, you just assume that m equals 1. So m equals 1 is the distance between that central maximum and that mixed line, and this is symmetrical. So if you have m equals 1, it could be going to the left, it could be going to the right, it doesn't make any difference, it's symmetrical. So, but unless you're told something different, you just assume that m equals 1. And all the m is telling you is basically how far out you go. 2, 3, 4. The farther, the bigger m is, the farther you are from the central maximum. Okay? Don't flip out, that's all it means. So then you have L, okay? So L is the distance that travels, and then you also, there's a wavelength in there as well, and then D is the distance between the gaps. Now, what you'll notice here is that you don't have the thickness of the opening, right? That's not a variable in this. What you have is the distance between the central openings in the screen. Now, obviously, if you're trying to do light and you have two, sheets of plywood as your opening, hey, this isn't going to work, okay? This obviously has to be a pretty small opening relative to the wavelength, okay? You're not going to get this effect if you shine a laser on two openings inside of sheets of plywood, okay? It has to be small relative to the wavelength that you have. Okay, so here's what I want you to see, and I apologize, that lambda got lost in there, that m lambda L over the equals delta y. So that's the one big equation. The other one, and this is what you need on number 7, is this d sine theta equals m lambda. So what's happening here in terms of why the wavelength is a part of this? Because if you have two openings and that light is coming through both of them, for them to reinforce that point, it has to match up where the wavelengths have constructive interference. And the only way that happens is if the wavelengths are basically meet at the same point on when it hits through that screen. That's how you reinforce it each other. Now, if it's straight on, that isn't the problem because there's no angle to worry about. That's that central maximum. Where you get a variation is when they're going to travel different lengths. Now, because of the fact that you have these two openings, one is going to travel longer than the other one is. But the difference in whence and how that's going to travel has to be a multiple of the wavelength because it has to reinforce each other. So it might be off by one wavelength, it might be off by two wavelengths, three wavelengths, something like that. But it can't be off by a half because if it's off by a half, then you're not going to have constructive interference and it's not going to produce a bright light. So that's why this multiple of the wavelength has to be in here. So on number 7, and they give you a whole bunch of information, 2 narrow slits are 50 mm. So let's start with this. What's the mu stand for? Micrometers, okay? Very, very small distance, okay? Are illuminated with light with a wavelength of 500 nanometers. What's the angle of the m equals 2 bright line fringes in radians and degrees? And that's why I say just give this in radians. Or in degrees, the radians don't make much sense. So on number 7, all you have to use is this d sine theta. Now, again, this d is not the thickness of the opening. It's how far apart the openings are. And you always have to be in the same unit. So m is going to be, again, that m has to be a whole number integer. It has to be 2, 3, 4, something like that. So this side over here, this m lambda, and if you look down that set of equations on your equation sheet, a lot of things equal m lambda. And the reason that it's m lambda and the reason that that m is a whole number multiple is because, again, it has to meet wavelength to wavelength. It has to meet like trough to trough or crest to crest. They have to reinforce each other. That's why you can model sound, and that's why I did that sound lab. Oh, right. You reached that point where that sound got really loud. Okay? So that was like a multiple, in this case, the sound is like a fourth of the wavelength. But it's where that reinforces each other and it got really loud. In light, that's where it gets really bright. So that's why that's that common theme that's like in lambda because the wavelengths have to match up. So when you get to, so that's just a simple algebra problem. The angle is like really small. But practically, if you look at this, let me rewrite this a little bit. So if you look at that d sine theta equals m lambda. And this is what I said. Practically, this is a cool equation in terms of finding the wavelength of light. Because we can't physically look at a beam of light and go, oh, we'll just take a picture of it, and then we'll get the photon here, we'll get the photon there, and we'll measure the wavelength. Cool. No. Okay? Number 1, it's traveling at the speed of light. Number 2, you can't really take a picture of the photon with another photon because that just looks weird. So in terms of measuring the wavelength, we can't. But what we can do is that we can shine light on a whiteboard like I did back there, and then I can measure the angle from where that opening is over to that edge. Hey, that's a number I can work with. I can find the sine of an angle. I can figure out how far apart the openings are in the aluminum foil. Oh, I can get that number. If it's the first bright line, m's going to equal 1. Okay, cool. So the left side of that equation are things that we can easily measure. And from that, we can figure out what the wavelength is. Okay, that's how you get the wavelength of light. Okay, cool. Now, when you get to number 10, same setup, light wavelength of 600 nanometers. So let's do a little comparison of 7 and 10. So on number 7, you have a 500 nanometer wavelength, and on 10, you have a 600 nanometer wavelength. Okay? So this other big equation that delta y equals m lambda L over d. Let's talk about this. So a little comparison up here. So let's say that I have a setup like this where I have the 2 openings. And here's my screen. So this is my value of L. That gap in between the openings is D. So which one of these two, the 500 nanometer or the 600 nanometer, would have the bigger gap between the bright line magnification, where it's really bright, that reinforcement? The 500 or the 600? Okay.
600?
I have the same opening.
Oh.
I can either shine 500 nanometer light on it, or I can shine 600 nanometer light on it. Which one over here on this screen is going to have the bigger gap between the bright lines where you see intense light? The 600 or the 500? 600. Why? Bigger. Look at the equation, right? It's m lambda L over d. L is the same for both of them because that's the distance between the screen and the whiteboard. D is the distance between the gaps. That's the same. So as your wavelength gets bigger, the gap gets bigger. Okay? And hopefully that could make sense. Because again, I hate to beat this drum too much, but the reason that lambda is there is because of the fact that it has to have constructive interference. So if those wavelengths are bigger, then you're going to have a bigger gap between when they reinforce each other. Okay? Cool. Now, so on number 10, you've got the 600 nanometers, that's your wavelength. Are spaced 1.8 millimeters apart on the viewing screen. So you have to get this idea. What does the 1.88 millimeters represent in this equation? The delta y, the lambda, the L, or the lowercase d?
Delta y.
That's your delta y. That's how far apart those bright lines are existing. Okay? Cool. That's that number. So you've got the 600 nanometers. Now, 600 nanometers, here's the easiest way to deal with that. What does nano mean? Well, I got that.
Billion.
What does nano mean?
Small.
Brilliant, Big Mike.
E to the negative 9.
He's right.
He's not wrong.
Yeah.
It's just that I guess I should have quantified that. How small does nano mean?
10 to the
10 to the negative.
9.
So when you're dealing with light and you have nanometers, it's just about as easy. You can just write it as 600 times 10 to the negative 90. Okay? That's just an easy functional way to do that, is 600 times 10 to the negative 90. Okay. So on number 10, what you're searching for then, what will be the fringe spacing if the light is changed to a wavelength of 400 nanometers? So obviously, on that first one, you have a fringe that's 1.8 millimeters apart. So if I shrink the wavelength down to 400, what should happen to the gaps between?
They decrease.
So right away, you know your answer to number 10 has to be less than what?
18 nanometers.
Yeah, it has to be less than the 1.8 millimeters.
1.8 millimeters.
Okay? Now, if you want to do a little bit of an algebraic trick, as long as it's the same setup, that ratio of L to D will be the same. Okay? So you really don't need it because of the fact that if you're making a comparison,
I know.
this ratio of L over D is going to be the same thing. Because you're not going to change the length to the screen, and you're not going to change the distance between the openings.
Okay, what is M? What does M stand for again? Like intensity or something?
Doggy's been over it.
No, it has to be M, so like.
Okay. M tells you, it's an integer that tells you basically how far away you are from that central bright line spectrum. So if this is the central line, that's the brightest. So if you're at the first bright line, M is going to equal 1.
Okay.
If you're at the next one, M is going to equal 2.
Oh, okay.
Do we assume it's just 1
Unless you're explicitly told differently, you assume that M equals 1.
Okay.
Okay? So obviously your answer to number 10 should be less than 1.8 millimeters.
Mr. Burkhead, what's the homework situation?
You have the test, you don't have any homework.
Oh, I forgot it.
And no calories are.
And no chem homework.
No homework.
You know I have it in priority.
Well, unless you have the test. Okay, now let's talk about number 12. So number 12 is either the most difficult problem on here or it's the easiest, depending upon your perspective.
Mine was pretty simple.
Okay? So you've got two narrow slits, 0.12 millimeters apart, light of wavelength decay, causing interference pattern. Light from each slit travels to the end equals 1. How much farther did the light from the left travel than the one from the right? Now, this is why I've preached and preached and preached. The answer to number 12 boils down to m lambda. Okay? And the distance that they travel has to be a difference of what? Wavelength?
Multiplication of the wavelength.
That has to be a multiple of the wavelength, right? Okay? So, on number 12, you can make 12 horribly difficult, or you can look at this and go 550. So the answer to number 12 is just 550. Because all it asks for is how much farther does one travel than the other. And it has to be a multiple of the wavelength. Yeah. So your answer to 12 is just 550.
No unit?
That's no answer.
I'm like, no unit.
Yeah. Okay.
Yeah, I have an answer. I'm close.
Yeah, look at this one.
It was a week, right? It's 550.
Okay. Now, let's talk about those first problems on 1 through 4. Okay?
Actually,
So,
5.
there's a couple of things about index of refraction. Okay? So, the smallest possible value of index of refraction is 1. Okay? That's the smallest possible index of refraction that you can have. The bigger the index of refraction is, the more it slows down in that medium. Okay? So, there's a couple of ways you can look at this. One is to realize that the new velocity in the new material is the speed of light divided by n. Okay? And n is that index of refraction. So, if n equals 1, what's the velocity in the material? It's the speed of light, right? 3 times 10 to the 8th meters per second. So the bigger n is, the smaller the velocity is. Okay? So that's going to be one main idea. The bigger n is, what we call it, we say the more optically.
It's a drag.
Adam put it
We
in
call him
my
a young
ear.
baby.
I didn't know what to do with it.
I don't even have my glasses on and it's annoying.
I can't do anything about it. I
Yes,
didn't
you
place
can.
it. It's nature. I didn't place it there.
Highlights.
Yeah, pencil.
It's a hot, yeah, it's a pencil.
Have you
Because
heard of the-
I'm his
have you heard of the
hairstyle.
Okay. Back to our story.
Newton's fourth law is direct.
So if n equals 2, what would be the speed in the new material?
Half the speed of
Half
light.
the speed of light, right?
Yeah.
1.5 times 10 to the 8. Still hauling the mail, still 10 to the 8 meters per second. It is like, oh, it's just half the speed of light. I can do that. No, you can't.
I could do that.
No.
I couldn't.
Okay. So that's going to be part of it. So as n increases, the velocity decreases. Okay, so that's part one of the story. That's part one. Now, the other part of this story is the idea that the speed of light equals wavelength times frequency. So this is in a vacuum. In a vacuum, in a vacuum. Okay? So that's 3.00 times 10 to the 8th meters per second. So there's different chapters to this story that we all have to put together. So, speed of light, wavelength times frequency, 3.00 times 10 to the 8th meters per second. The other page in this book is E equals H times frequency, or E equals H nu, depending upon how you want to write this. So, this is something that you remember. The energy of light is determined by the frequency of the light, and that determines the color. Okay? So if you compare like purple light to red light, red. Okay? So as you go across this spectrum, if you've heard like the Roy G. Biv, red, orange, yellow, green, indigo, violet, okay? So red light relatively has a very long wavelength. Purple light has a very short wavelength, okay? But they all travel at the same speed of light. So if purple has a very short wavelength, what do you know about its frequency?
It's super high, like ultraviolet light.
High frequency red light has a lower frequency. So which one's going to have more energy? The purple light or the red light? This is going to have higher energy. This is going to have lower energy. Okay? Now, so this is also why sunsets appear reddish oranges, is because if you look at the Earth and when the sun is setting, that light has to travel through much more of like our atmosphere because it's running parallel with the surface. So when the sun's overhead, that light's just coming through here. But when you're looking at a sunset, that light has to travel through much more of our atmosphere. So the reason that sunsets appear red is because red light has a longer wavelength. It doesn't get scattered like the higher, like the shorter wavelengths do. So if whether it's a sunrise, sunset, whatever, they're typically red. And especially in the wintertime, if you've seen some of the sunsets lately, like the sky appears like it's on fire. Okay, it's like a really, really bright red sky, because of the fact that that red light is still making it through and the other colors are being scattered.
Okay, Bert, one time it was nighttime, pitch black outside, and the moon was completely red. What happened?
It's just we just supposed to have a lot of dust in the atmosphere.
Oh. All right, Alpha, settle down.
Okay. So, what determines that this looks, yes?
Wait, so is white light the fastest or is that the slowest?
Oh no, they all travel at the same light. They all travel at the exact same speed.
So then what's white?
White light is just a blend of all the different colors. Okay?
So then how does some
What about black light?
first?
How does what?
Then why can't you just like purple and then like, why is it white?
I'll show you in just a second. When we go back, I'll show you why.
We're gonna go back.
Okay? Now, So, here's the odd thing about why this appears red. This appears red because it's actually every color but red.
Actually?
No, it is. So this appears red because it absorbs purple, green, all the colors of the spectrum. The only color that it doesn't absorb is red, and that's what gets reflected off. This cup appears purple because of the fact that it absorbs every color but purple. Now, Davmai, if you're wearing something of a very dark color, that appears a dark color. Why? Because it absorbs basically all of the colors.
Yeah.
Okay, it doesn't reflect anything off.
Is that good?
White colored clothes, what does that do?
Absorbs nothing, reflects everything.
Yeah, it absorbs nothing, reflects it. So in the summertime, why don't you want to wear like a black shirt outside?
Don't even
It's
try
going
it.
to absorb all of that energy.
albedo effect.
No, kind of, not. But if you wear a light colored shirt, what's it going to do? It's going to reflect most of that energy off. So this is what I find absurd. And this is a small editorial statement. So more and more, like if you see houses, they paint them black. And all the physicists in the world are going, are you people just idiots? Because if you have a black colored house, what's it going to do in the summertime? It's just going to heat up. It's just going to absorb all of that energy.
For aesthetics, Barry. For
I don't
aesthetics.
care.
Black is stupid.
God.
Black is
white
Sorry.
stupid.
Small editorial comment on people painting their houses black. Okay. So,
Change my plans now.
back to our story. So, what determines color is frequency, not wavelength. Frequency determines color. So, you take light and you send it through an optically dense medium, say n equals 1.5, whatever that is. Okay? So, the velocity in that would be the speed of light times 10 to the 8th meters per second divided by 1.5. Right? So that becomes a new velocity, it becomes less. But that velocity also equals wavelength times frequency. So if I take this red ball and I put it on this side, does it still appear red?
Yeah.
Why?
Frequency didn't change.
Frequency did not change. So if I have a smaller velocity and the frequency stays the same, what's the only way that happens?
Down.
Wavelength down.
Wavelength becomes smaller.
Yes.
Now, here's an interesting thought process. So you set up a double slit experiment. Okay? Light comes in, and you get your bright line spectrum over here. Okay? I take that same apparatus and I submerge it in water. What's going to happen to the spacing?
Let me think of my equation sheet.
It's gonna decrease.
According to my calculation.
They're closer.
I think it's
It's
smaller.
not
Closer together, right?
No.
It'll decrease.
Okay.
Oh, it decreased.
If I put it in water,
Water.
Delta Y.
so what happens to the wavelength in water?
Oh,
It goes down.
So the spacing gets closer.
Yeah. Just
Final
double.
answer.
So the spacing would get
Closer.
I'm just saying this is
Real skeleton answers.
On the test, second question, answer C.
I'm just saying it's something to think. Okay?
Yeah, Bert,
It
can
might be a question like number 4. Yeah.
we go over the test questions?
Just
and
chill
answers?
out.
Yeah, we go over the answers.
Can I just get the answer sheet?
Okay.
Can I take a picture of it?
So on question number 4, or problem number 4, excuse me, we're defining that new velocity. That should be horrible GPA times 10 to the 8th.
This one?
On 4, problem 4.
Velocity, what were you finding?
On A.
Bro,
Yeah,
it's
okay. Yeah. Because I was
Uh,
looking at B, I was like, that's not horrible.
all right, any questions on the assignment? Once, twice, so.